Hi everyone, welcome back to this lesson. We're going to be looking at trigonometric integrals. Now, these trigonometric integrals that we're going to be looking at are going to be of the form, as you see on screen here, sine to some power times cosine to some power of x. And depending on what the powers are for either sine or for cosine, it's going to lead us into a different path to evaluate that specific integral. So on here you have three separate cases. You have case 1 where m is odd. In other words, the power for sine is going to be odd. So you could have sine to the power of 3, or sine to the power of 5, or sine to the power of 7, so on and so forth. What we want to do is we want to split off one power of sine and use the Pythagorean identity for sine squared of x is equal to 1 minus cosine squared of x to express the remaining powers of sine of x in terms of cosine. And then we use the u substitution that is given here. Now, we also want to go through the process for case number 2. And case number 2 in here is going to be where we have n is odd. Now, I just realized on case number 1 I wrote dv, and that's actually supposed to be du. My apologies there. There we go. Du is equal to negative sine x dx. Now, case number 2. Case number 2, we are looking when n is odd. And n being odd is going to be when the power of cosine is odd. In order to evaluate this, then we split off one power of cosine, and then we use, again, similar Pythagorean identity for cosine squared x is equal to 1 minus sine squared x, and we express the remaining powers of cosine of x in terms of sine of x. Then we substitute u is equal to sine of x, and therefore du, my apologies, du is going to be equal to cosine of x. And then we have one final case. The final case here is going to be where m and n are both even. If they are both even, then we either use one of the double angle formulas repeatedly, or we convert the integrand into an expression entirely in terms of sine and cosine, and then apply the reduction formulas. And we'll talk about the reduction formulas in just a bit. So, moving forward. We're also going to be looking at trigonometric integrals of the form tangent to some power of x times secant to some power of n of x. And in this particular case, again, we have three different versions or three different cases. Case 1, m is odd and the n value is greater than 1. In this particular case, we're going to separate out the factors, or the factor secant x times tangent of x, and we're going to use the identity tangent squared of x is equal to secant squared of x minus 1 to express the rest of the integrand in terms of secant of x. Then we're going to use the substitution u is equal to secant of x to obtain the integral involving only powers of u. Case number 2, we do it very similar, but here we're going to be looking where n is even. We then separate out a factor of secant squared and use the identity secant squared x is equal to 1 plus tangent squared of x to express the rest of the integrand in terms of tangent of x. Then we use u is equal to tangent of x to obtain an integral involving only powers of u. And finally, we arrive at case number 3. Case number 3, where m is even and n is odd. In this particular case, what we do is we use the identity for tan squared x is equal to secant squared x minus 1 to obtain an integral involving only powers of secant x, and then we use the reduction formula. Now, you might be asking, well, Mr. Castro, what are those reduction formulas? Well, in order to talk about the reduction formulas, we first need to talk about the Pythagorean identities. We must know these Pythagorean identities as we progress through our time in calculus. So, you must be able to recall these Pythagorean identities at any given time. Sine squared plus cosine squared x is equal to 1. tan squared x plus 1 is equal to secant squared x. Cotan squared plus 1 is equal to cosecant squared x. Now the power reduction formulas. And these power reduction formulas are only going to be for the square values of sine and cosine. In order for us to be able to talk about these power reductions for sine and cosine, what we want to do is we want to use these double angles. So if you notice, we have these double angle formulas that I'm removing from the screen. And what we want to do is we want to use these double angle formulas to extract what a power reduction for sine squared is going to be. So looking at sine squared, if we use the power reduction that we just had on screen, what we're going to do is we're going to solve for sine squared. Now, solving for sine squared is going to get us 1 minus cosine of 2x, and this is going to be multiplied by 1/2. So this is one of the power reduction formulas that we get to work with. And again, it's a power reduction because we take the sine squared and we essentially replace that sine squared with its equivalent form by using those double angle identities. And in that sense, sine squared of x is equal to 1/2 times the quantity of 1 minus cosine of 2x. We do something very similar for cosine squared of x. So for cosine squared of x, we're going to take the double angle identity once again, and we're going to solve for cosine squared of x. And in this particular case, we get 1 plus cosine of 2x. And any time that we want to look at some power reductions where we are trying to integrate some form of sine squared or some form of cosine squared, then we must always use these specific power reductions. And these are going to be important for you to know. That's why I outlined these in red. And then finally, the integrals to know moving into this section and progressing through the course. We're going to need to know what is the integral for tangent of x. That one we've derived to be the natural log of the absolute value of secant of x plus a constant. And we must also know the integral for secant of x dx. This is going to be equal to the natural log of the absolute value of secant x plus tangent of x. And then we have plus a constant. Anytime that we see one of these integrals that we're supposed to know already, so integral for tangent or integral for secant, we can go through to the end result and identify that that integral will evaluate to one of these answers. And again, Pythagorean identities, we must know those, and the power reduction for square values we must know as well. So let's move into these evaluations of integrals, and we're going to see how we're going to be employing all of these techniques that we just listed. So on this integral, I want to integrate sine cubed of theta multiplied by cosine to the power of 4x, and this is going to be dx. Now, if you look all the way from the very beginning, we then go through these different cases. Well, we have that sine is an odd power. So we're going to use case number 1. We're going to split off 1 power of sine of x, and then we're going to use that Pythagorean identity to make our replacement. So that's exactly what we're going to do here. Break off 1 power of sine, so we get sine of theta multiplied by sine squared of theta multiplied by cosine to the 4th. Oops, I wrote theta and x's here. I don't know why I wrote x's. My apologies, it got mixed up here. Cosine to the 4th theta d theta. There we are. And then here, again, sine theta times sine squared times cosine to the fourth theta d theta. Now we're going to make our replacement for that for that Pythagorean identity. That Pythagorean identity will then be here, sine of theta multiplied by 1 minus cosine squared theta multiplied by cosine to the fourth theta d theta. Now is when we can make the substitution. So we now go through the whole substitution process. All right, so we're going to go through the whole substitution process. Now, before we go into the substitution, I want you to recall that whenever we have some trigonometric function as, let's say, sine cubed of x, then this really means that we have sine of x to the power of 3. And again, this is just the notation that we use. So when I go and make my substitution, I want to make my substitution in this particular case as u is equal to cosine of theta. In this case, because du is going to be negative sine theta d theta. Now that's going to be really good. That's negative du, and this is going to be sine theta d theta. And again, I say that's good because at this time we have sine of theta. So again, we have this sine of theta d theta, and that's going to be my new negative du. Now I also have in my factors, I also have this 1 minus cosine squared, but remember, cosine is now u, so this is 1 minus u squared. Cosine to the fourth, remember we're using this process where cosine to the fourth theta, or cosine to the fourth x, will now just be the quantity of that cosine. But cosine is u, that means we have u to the power of 4. And then that sine theta d theta is that negative du. Well, we go through with our evaluation process. We're going to have negative integral, and then we distribute u to the fourth as such, and then we have negative times a negative will be, negative's out here. My apologies. Since the negative's out here, you know what? Let's leave the negative inside. Change of heart. Negative inside. U squared times u to the fourth, that's going to be u to the 6. Negative and negative, that's a positive, which means that's going to be u to the 6 minus u to the fourth, and that's going to be du. Now, that's a polynomial that we can integrate, so we just integrate. That's 1/7 u to the 7th minus 1/5 u to the 5th plus a constant. But at the beginning, we weren't dealing with u's, so we're going to resubstitute. And now we have 1/7 multiplied by cosine to the power of 7, this is theta, minus 1/5 multiplied by cosine to the 5th theta plus the constant. And there we have it. That's pretty much it. So again, as long as we follow the process, as long as we follow those techniques, this should lead us into something that we can actually integrate and something that we can actually do. So let's look at part B. I want to integrate the integral from 0 to 2 pi for sine squared of theta divided by 3, and this is going to be d theta. Well, here we have sine squared divided by theta over 3. So what I'm going to do is I'm going to use those power reduction formulas that I was just talking about right above, right here on the top of your screen. So I'm going to use that to reduce this sine squared power in order to make sure that we arrive at the appropriate answer. So let's go ahead and let's work with that. So using my power reduction, notice that your theta here is, your argument is theta divided by 3. So we have to make sure that we account for that when we're making our substitutions. So making this, or not substitution, but making this replacement with this identity. So I have 2 pi, 0 to 2 pi, and this is now going to be 1/2, because sine squared theta divided by 3 is equal to 1/2 multiplied by 1 minus, this is going to be cosine of 2 times the argument. So 2 times the argument is 2 times theta over 3, and this is going to be d theta. Okay, let's keep going. The 1/2, that's going to be a constant. Let's factor that forward. So that's 1/2 multiplied by the integral from 0 to 2 pi. And now we have 1 minus cosine of 2/3 theta d theta. So now all we do is integrate. So when we integrate, integral of 1 with respect to theta will then just get us theta, minus the integral of cosine will then get us sine of the same argument, which is 2/3 theta. However, we have to then divide by its by its argument coefficient, which is 2/3, or in other words, if we're dividing by it, we're going to multiply by 3/2. And this is because when we take the derivative of sine of 2/3 to get us back to this integrand, we then have to multiply by the derivative of the inside by the use of the chain rule. Since the coefficient in the integrand is a 1, when we're subtracting that cosine, we need to make sure that we counteract that whenever we integrate it. So once we have this, we then evaluate from 0 to 2 pi. And again, we have a half, so this is 1/2 multiplied by 2 pi minus 3/2 times sine, and this is going to be 4 pi thirds minus 0 plus 3/2 sine, so 3/2 sine at 0. Okay, that's nice because this last portion just goes away because sine at 0 is just 0, which means we're only left with these initial values. So as we go through, distribute the half, this will now just get us pi minus 1/2 times negative 3/2, that's going to be negative 3/4, multiplied by sine of 4 pi thirds. So sine of 4 pi thirds, that's going to be in the third quadrant. So if it's in the third quadrant, sine is going to be negative in that third quadrant. There we are. So negative times a negative will then be positive. And sine at pi thirds, that's sine at 60 degrees, that's going to be root 3 over 2. So that's negative root 3 over 2, and we already accounted for that negative, so there it is. So now all I get to do is simplify, and the simplification here gets me pi plus 3 root 3 divided by 8. And there's your final answer. Pretty good. Pretty straightforward. I like that so far. All right, we're going to keep going. All right, so here's your part C. For part C, we want to evaluate the integral from 0 to pi halves for 2 minus sine of theta to the power of 2 d theta. Now, looking at this particular integral, we can't exactly make a u substitution, or we can't exactly do any type of integration directly. So what we want to do instead is we want to expand this binomial. And so what we're going to do here is we're going to distribute this binomial into itself. So 2 squared, that's going to be 4, minus 2 times 2, again, that's going to be 4 sine theta, and then plus sine squared theta, and that's going to be d theta. Now, from here, we can do term-by-term integration. However, we have to be careful because we see a sine squared. And from that sine squared, we want to make sure that we can integrate that sine squared. So we're going to make the power reduction substitution, which will be 1/2 multiplied by 1 minus cosine of 2 theta d theta. Perfect. So again, this substitution, sine squared, was this power reduction. Everything else stayed the same. Now I'm going to combine my like terms. So like terms here, I have 4 and I also have 1/2. So when I take 4 and I add 1/2 to it, I should get, in this particular case, 9/2. So I get 9/2 minus, that's going to be 4 sine theta, minus, again, this half distributed, so I get 1/2, so minus 1/2 cosine of 2 theta, and this is all d theta. Okay, now we can go term by term integration. Integral of 9/2, that's going to just be with respect to theta. That's 9/2 theta. Integral for negative 4 sine theta, that's going to be positive 4 cosine theta. The integral for negative 1/2 cosine squared, or sorry, cosine 2 theta, that's going to be negative 1/4 sine of 2 theta. And this is all evaluated from 0 to pi halves. Now you can double check. If you take the derivative for negative 1/4 sine 2 theta, we should get negative 1/2 cosine 2 theta. And making our substitutions, so 9/2 multiplied by pi halves plus 4 multiplied by cosine of pi halves minus 1/4 multiplied by sine of pi, because 2 times pi halves is pi, minus 9/2 multiplied by 0, minus, because we're subtracting all this, 4 times cosine at 0, and then plus 1/4 sine at 0. Now I'm going to simplify this as much as I can. 9/2 multiplied by 0, that's going to be 0. Okay, that's not too bad. Sine of 0, again, that's 0. Cosine of 0, that's 1, so I can't simplify that, so let's keep that in mind. However, sine at pi does get me 0 once again. And when we're looking at cosine of pi halves gets me 0 once again. So there is a lot of terms that cancel here, and we're then left with 9/4 pi minus 4 as our final answer. There you are. Pretty good. Pretty good. Okay, so again, integrals like this we should be able to do, and my expectation is that you should be able to do these either on a quiz, exam, or on a homework. Now let's keep going, and again what we want to do is we want to evaluate the integrals. And one of the first integrals that we're going to be looking at is part A here, which is going to be the integral for tangent squared of x multiplied by cosine cubed of x dx. All right. Now, in this particular case, you're going to see that this particular integral doesn't really satisfy one of the other integrals that we're initially looking at. All right, so we then got to keep that in mind. However, this does actually simplify kind of nicely if we express tangent as your quotient identity as such. And in doing so, we now get the integral of sine squared x multiplied by cosine of x dx. So check that out. That's not a bad integral. That's actually a pretty good integral that we get to see. And in here, all we need to do is just make a really quick substitution. What we're going to do is we're going to call u is equal to sine of x, and therefore our du will just be cosine of x dx. And in that process, well, sine squared of x, that's going to be u squared. Cosine x dx is just du. Wow, look at that. That's pretty good. We go through, we make our substitution. We integrate 1/3 u cubed plus c, and we finally make our overall substitution. That 1/3 is multiplied by sine cubed of x plus c. And there you are. Pretty good, pretty straightforward. I like it. Let's keep going. Let's try part B. So for part B, I want to work on the integral for tangent to the 5th x times secant cubed x dx. Now, this one in particular, we're going to have to use those properties that we were looking at before at the very beginning of this section. So I'm going to scroll up all the way, and we're going to take a look at these properties, and we're going to see which one this is going to fit. Okay, so then we just start cross-checking which case would this satisfy. Again, that integral that we're looking at is tan to the 5th x multiplied by secant cubed x dx. Well, the power on secant is not even, so that's not case 2. So in that particular case, we're going to be looking at either case 1 or case 3, but in case 3 it says that m is even, and that's false for the problem that we have, which means we're going to be looking at case 1. So case number 1 says separate out the factor of secant x times tangent of x, and then use the identity tan squared x is equal to secant squared x minus 1. Okay, so let's go ahead and let's do that. We want to factor out a secant x times tangent of x. So let's give that a shot here. Okay, so this is going to be the integral for secant of x times tangent of x. Okay, I'm going to factor that out. Multiplied by, let's see, I took out one tangent, so this is now going to be tangent to the 4th of x. Okay, secant, I'm now working with secant squared x as such. And again, if we distribute all this, then we have tan to the 5th and secant to the 3rd as well. Okay, and this is all going to be with respect to dx. Now again, once we have all this, as we can see up here, now we're going to express the rest of the integrand in terms of secant of x. So making sure that we express the rest of the integrand in terms of secant of x, what we're going to do is we're going to take tangent to the 4th and we're going to re-express that. So secant x times tangent of x, and re-expressing tangent to the 4th, what we're going to do first is we're going to do tangent squared of x, all that squared to the power of 2, or squared, and then we have secant squared x dx. So all I did was I rewrote tangent to the 4th. And the reason I wanted to rewrite tangent to the fourth is because I am now going to use the Pythagorean identity that says when I have tangent squared theta, this is going to equal to secant squared theta minus 1. In doing so, I'm going to replace this tan squared with that Pythagorean identity, substitution, which is secant squared x minus 1 raised to the power of 2 multiplied by secant squared of x dx. Now you might be saying, wow, that's a lot of work there. And you're right, that is a lot of work. However, we are now at the point that we are looking at this in order to make a really good substitution, and everything should start unraveling from there. So what's the substitution that we're going to make? That substitution is going to be secant of x. And the reason we're going to make the substitution is because when we take the derivative of secant, we're left with secant of x times tangent of x dx. And in that sense, that is why we wanted to pull off one of those factors that contains secant of x times tangent of x. That way we could make that substitution. So now secant of x times tangent of x dx, that's all going to be du. In my parenthesis here, secant squared, that's now going to be u squared. So that's u squared minus 1 quantity squared times secant squared. But remember, secant is now u, so this is going to be multiplied by u squared. And then the remainder, which is secant x tangent of x dx, that's all du. All we need to do now is expand this binomial. All right, that's not too bad. So let's go ahead and let's expand this binomial and let's distribute. So this is going to be u to the fourth multiplied by u squared. So that's going to be u to the 6 minus 2 times, well, this is u squared and u squared, so that's going to be u to the fourth. Perfect. And then plus u squared. That's all du. Which means we now have a polynomial to integrate, and we can integrate this term by term. U to the 6 now integrates to 1 over 7 u to the 7 minus, this is going to be 2/5 u to the 5th plus 1/3 u to the 3rd plus your constant. But then again, at the end of the day, we weren't integrating with respect to u, so we're going to resubstitute our value, which will get us 1/7 multiplied by secant to the 7th x minus 2/5 secant to the 5th x plus 1/3 secant to the 3rd x plus c. And there you are, ladies and gentlemen. That is your integration for this particular integral that we were given. Okay, not too bad. Wow. And I say not too bad, just being mindful of that as we're looking at this, some of these integrals can get bad, and they can look very bad. They can look very intimidating, but again, we have to make sure that we don't back off these integrals and that we put in the right amount of work in order to extract the answer that is needed. So let's go ahead and let's try a few more. Let's try part C. So here goes part C for this integral. I want the integral of x times tangent squared x dx. Now, this type of integral, well, yeah, we haven't seen this type of integral here, and you know what? It's okay. It's okay that we haven't seen it. So what we're going to do is we're going to try to see what we can integrate and what we can't integrate, and then we'll go from there. Okay, so here we go. Substitution won't work. Trigonometric integral will not work because we don't have a version of tangent squared multiplied by secant to some power. So trigonometric integral doesn't work. U substitution doesn't work, which means by parts might be our friend here. So we now have to anticipate. Well, I was about to say anticipate. Wow. Okay, so we now have to anticipate what we might be looking for here when we're talking about x multiplied by tangent squared of x in order to identify that particular integral. All right, so let's go ahead and let's talk about that. All right, so as we're looking at this, we're going to see that as we start trying to pick our u substitution, I think I want to choose my u substitution as my x. Therefore, when I take my derivative, my du is just going to be dx. And now it might not be very apparent at this point in time, but this is actually going to set us up real nice. And the reason why it's going to set us up real nice at this time is because now we get to choose our dv. And our dv is going to be tangent squared x dx. And so we then have to figure out an antiderivative for tangent squared x dx. And the antiderivative for tangent squared dx, well, we're actually going to work with that a little bit down below. Okay, so I want to make sure that I work with this very efficiently. That way we can extract the items that we're looking at here. So when I integrate, or when I find the antiderivative for tangent squared of x dx, this antiderivative will then have to be integrated as the Pythagorean identity for secant squared of x minus 1 dx. And once we're able to extract this piece, well, then here, what I get to do is I then get to integrate term by term. In other words, we then get to integrate secant squared x dx minus integral of 1 dx. And the antiderivative for secant squared of x, well, that antiderivative is kind of nice because that antiderivative is just tangent of x, because the derivative of tangent is secant squared. So that's pretty good. And then minus the integral of 1x with respect to x, so that's just x. Which means that my antiderivative, the one that I'm looking for, my v value, is going to be tangent of x minus x. And so again, this was the antiderivative. So again, at first it might have seemed that we didn't make the right choice. However, once we explore that option, then we're actually left with something real nice. So all we then need to do then is u times v minus the integral of v du. So we're going to go u times v. So this is going to be x multiplied by tangent of x minus x minus the integral of v du. So that's going to be the integral of tangent of x minus x, and this is going to be dx. All right, that's not too bad now. So let's keep going. Let's distribute x times tangent of x minus x squared. All right, looking pretty good. Now we're going to distribute here the integrals, so that's going to be minus the integral for tangent of x dx plus the integral for x dx. And remember I said that that integral for tangent of x we needed to know, and there's that integral for tangent of x. So again, we must know that from the very beginning, and this is now x times tangent of x minus x squared. All right, this integral for tangent of x, remember that is the natural log of the absolute value of secant of x. There we are, so minus natural log of absolute value of secant of x, pretty good. And then the integral for x, well, that's just going to be plus 1/2 x squared. And all of this are indefinite integrals, so we need a plus c. Condense all of our like terms, x times tangent of x, and then we have our x squareds, which will be negative 1/2. So let's rewrite this, x minus 1/2 x squared, there we are, looking pretty good, minus natural log of the absolute value of secant of x plus c. And there you are. We've evaluated that integral. Very nice, neat, and concise. And again, that's a work that I am looking for when I am trying to expand or evaluate these given integrals. So that is going to be it for now, and I hope that you all enjoyed this particular lesson, and I hope that you all stick around for the next lesson, and I will see you all next time.